Let's continue with the example, the tree example that we were discussing last class. And I know from past experience that some students find this difficult. So let's try to go through it slowly. To repeat the problem we're dealing with, suppose the future value of trees increases according to this formula, A times e to the square root of t. Now notice this is not v equals a times e to the rt. This is different, because the trees will grow according to their nature and according to how much rain they get. And let's just assume that this formula right here accurately describes the growth and the value of trees, the future value. Okay. And notice it's not, the trees are not growing at a constant growth rate in this case. If they were growing at a constant growth rate, then they would have fit into this formula right here. But, unfortunately, trees don't grow at a constant growth rate of r, so we can't use this formula. Okay. One of the characteristics of trees, if you noticed, you planted them, at first, the first few years, they grow very quickly. It's not unusual for them to double in size the first few years. But after the trees age a while, their growth rate continues, but it slows down. So it's not constant. Okay. So we couldn't use a formula like this. A formula like this assumes that the trees are growing at a constant growth rate of r, but they don't. They grow according to this formula. Okay. Now the question is, if the trees grow according to this equation, when should we cut the trees down? And the solution, as we discussed last class, is to find the value of t that maximizes the present value of the trees. Because money received in the future is not worth as much as money received now. So you want to cut down the trees to maximize the present value. And the present value is given by this formula. Now this a here in our problem was just 1,000. Okay. That is just the value at time 0. But more generally, the expression for present value would be this. A of t equals v of t times e to the minus rt, where r is the continuously compounded interest rate. Okay. And what we want to do is find a value of t that maximizes the present value. To get the present value, you've got to multiply the future value by e to the minus rt. Okay. So we just plug in. We assumed that our r value in the problem we did yesterday was 0.1. And if we just now substitute in for v is 1,000 e to the square root of t times e to the minus rt. Now, since these e terms are multiplied times each other, you just add the exponents. And this becomes equal to 1,000 e to the square root of t minus 0.1 t. Let's realize that r is 0.1. Okay, so we'll substitute that in. And let's do one more thing. Instead of writing this as a square root of t, let's use the equivalent expression, t to the 0.5 power. Because if you write t to the 0.5 power, then you just use the power function rule to differentiate. Okay. So now this is in this form. A of t equals 1,000 times E, and let's just call this f of t, where f of t is this. Now, when you have an equation of this form, when you have some constant times e to the f of t power, the derivative of that with respect to time is just 1,000 times f prime of t times e to the f of t. Okay. So our first order condition is just this. 1,000 times f prime of t times e to the f of t. Okay. So we're just using that rule of differentiation. Okay. Now, f prime of t in this case is just t to the 0.5. F of t is t to the 0.5 minus 0.1 t. So f prime of t, its derivative is just this, 0.5 t to the minus 0.5 minus 0.1. So that's what we substitute in here for f prime of t. Times e to the f of t, and f of t is just t to the 0.5 minus 0.1 t. Okay. Set that whole thing equal to 0. Okay. Remember, this up here is an exponent on e. Okay. All of that is an exponent on e. Okay. Now, the only way this expression is going to be 0 is if this term right here is 0. So that's the only way this expression will be 0, is if this expression within brackets is 0. Because this is never 0. Obviously, 1,000 is never 0. So the only way this equation can hold is if this expression in brackets is 0. So we get 0.5 t to the minus 0.5 equals 0.1. Just bring that minus 0.1 over to the right, and then solve for t. So we get t to the minus 0.5 equals 0.1 over 0.5. And this is just 0.2, isn't it? Okay. And now we have this equation right here, t to the minus 0.5 equals 0.2. We want t, so we raise both sides of this equation to the minus 2 power. So we get t to the minus 0.5, all of that raised to the minus 2 power equals 0.2 to the minus 2 power. Now, this rule for exponents, when you have an expression like this, you multiply the exponents. Okay, so this just becomes t. T star equals 1 over 0.2 to the 2 power. So t star equals 1 over 0.04 or 25. Okay. All right. So this suggests that the optimal time to cut down the trees is 25 years, if t is measured in years. Okay. Now, to be sure that this value of t maximizes the present value, instead of minimizing it, heaven forbid we should minimize it, we want to maximize it. So what should we do to make sure that this value of t equals 25, maximizes the value of the trees? So if you minimize the value of the trees, you select a time that minimizes the value of trees, you're likely to lose your job. So you want to make sure you maximize the value of the trees. So how can we be sure that we're maximizing the value of the trees instead of minimizing them? I know you all know this. Okay, find the second order condition. Was that you, Heather? Sometimes I can't tell. Okay. So here is our objective function. Here's our objective function right here. The first derivative of this objective function is this expression right here. So let's forget the 0. The a prime of t is this. We want the second derivative. So let's just forget about this equals 0 part, because we don't need that right now. We needed that to get the first order, get the critical value of t. But to get the second derivative, we're going to have to, and let me do it over here, because this is kind of messy. This will test your skills of differentiation. See, I don't directly test your skills, but sometimes they come up in a word problem. So we want to differentiate this whole thing with respect to t. What rule of differentiation are we going to use? What's one of the rules we're going to have to use to get this derivative? The product rule. Because, exactly right, Dana. You see this expression right here is a function of t. But it's multiplied times another function of t. So we're going to have to use the product rule. Okay? So let's call this whole thing right here, this part right here, if we like, we could call that g of t, and call the second part h of t. So we have g of t times h of t. And using the product rule, we take the derivative of the first term times the second term plus the derivative of the second term times the first term. Okay? So let's do that. Take the derivative of the first term with respect to t. What is the derivative of this first term with respect to t going to be? Well, you just have 1,000 multiplied times this. So what is the derivative of this term within the brackets with respect to t? Patrick? Exactly. So you just take that, of course, times the 1,000. It's there. So the derivative of the first term is just 1,000 times, I'll put it in parentheses, what Patrick said, exactly right, minus 0.25 times t to the minus 1.5. Okay. That's the derivative of the first term with respect to t. Now we've got to multiply that times the second term, and the second term is just this, e times t to the 0.5 minus 0.1 t. Okay, so what we've done is the derivative of the first term times the second term plus what is the derivative of the second term with respect to t? Well, think of this exponent as just being f of t. So it's f prime of t times e to the f of t. So the derivative of the second term is just this. It's f prime of t, which I'll put in brackets, is 0.5 t to the minus 0.5 minus 0.1 times e to the f of t, which is this. And all of this is just the derivative of the second term with respect to t. Now you've got to multiply that times the first term. Okay. If you can do this, you're doing well. 1,000 times e to this 0.5 t to the minus 0.5 minus 0.1. Okay. All right. So again, derivative of the first term times the second term plus derivative of the second term times the first term. That's just the product rule. Okay. Let me just rewrite this and make this a little bit simpler. Minus 0.25 times 1,000 is going to be minus 250. So it's minus. Okay. Oh, you're right. I don't know why I put this e in here. Sorry. Thank you. This is just the derivative of the second term times the first term. The first term is just this. So you're absolutely right, Marshall. Thank you. Okay. Now, so this is minus 250 times t to the minus 1.5 times e to the t to the 0.5 minus 0.1 t power. Plus, notice you got this term here, 0.5 t to the minus 0.5 minus 0.1 times this, so that's squared. So you write this as 0.5 t to the minus 0.5 minus 0.1 quantity squared times e times t to the 0.5 minus 0.1 t, all times 1,000. Let me put the 1,000 first. Okay. Now we would like to show that this is negative. Now, obviously this first term is negative because of the negative sign. What about the second term? Yes, Diana? 0. Why do we know that second term is 0? Yeah. Why do we know this term within brackets has to be 0? Jay? Yeah, that was our first order condition. So if you notice that our first order condition was that this be 0, then the whole second term, as Diana said, drops out. And so let me just be careful here. A double prime of t0, or actually t0 is 25. Because we're looking at the value of the second derivative at the critical value. And at the critical value, this is just this. Okay. Okay. And clearly, that negative sign there means that that's going to be negative. So it is a maximum. So we are relieved. If we let these trees go for 25 years, we're actually maximizing the present value. Okay.